Free space management. So, in this chapter, we will discuss the algorithms of these allocators that we discussed in the previous videos. So, we will discuss still low level mechanism and policies that allows us to counteract those external fragmentation. Sorry about that. Of this memory. Uh, for segmentation. So we're trying to relax or getting closer on algorithms or policies that allow us to better manage our memory to make the operating system easier to use. So let's start. Um, let's make the problem more specific. Managing free space can certainly be easy, as we will see when we discuss the concept of paging. It's easy when the space you are managing is divided into fixed size units. So if the memory is a fixed size units, you just need to allocate that same size and you don't need to worry about any excess size, such as an allocated size in a process. But in this chapter, we will discuss how do we actually solve the variable size. For some process, you request that a lot of times, but for some process, you rarely request that. So how do we provide a priority queue? Because remember, the scheduler has this priority queue in which it handles the process to make it easier to use. So how do we provide that when it comes to virtual memory? Um, in such a case, you just keep a list of these fixed size units. When a client requests one of them, return the first entry. So for pages, structure of memory, because that's another form of virtual memory, it's easier. But here we will discuss a variable size of memory. How do we account for variable request, especially for malloc, for variable size request for our process? Where free space management becomes more difficult and interesting is when the free space you are managing consists of variable size units. This arises in a user level memory allocation library, as in malloc and free, and in an OS managing physical memory when using segmentation, like what we discussed previously, to implement virtual memory. So this variable size stems from, again, from the heap and from the unallocated space created by our segmentation. For dynamic reallocation, that's the earlier type of virtual form, but it's was replaced by segmentation to account for that unallocated space of memory, because it's too much space to waste. In either case, the problem that exists is known as external fragmentation. The free space gets chopped into little pieces of different sizes and is thus fragmented. So the reason why it is called external fragmentation is because space are chopped into little pieces of different sizes. Subsequent requests may fail because there is no single contiguous space that can satisfy the request, even though the total amount of free space exceeds the size of the request. So that's the problem we encounter in segmentation. Now we will try to see or find a low-level mechanism and policies such as algorithm, best fit, worst fit, uh, and any other algorithm that might help on our case when trying to build an operating system for this kind of workload that has different requests for size for each processes. So that's the one of the things that we were gonna solve here. The problem with divided space called external fragmentation. So it was created already before by segmentation. The figure shows an example of this problem. In this case, the total free space available is 20 bytes. Unfortunately, it is fragmented into two chunks of size 10 each. As a result, our request for 15 bytes will fail even though there are 20 bytes free, and thus we arrive at the problem we address in this chapter. How to manage free space. How should free space be managed? When satisfying variable size requests, what strategies can be used to minimize fragmentation? Because remember, our memory is limited. For example, we only have 16 gig. So process could uh, take that away in a contiguous form, right? In a priority style, such as heap. So how do we design our operating system in such a way that we don't have an allocated space, so we make good use of our limited memory? So that's the question. Assumptions. So we will again start with assumptions of our algorithm, and then we will relax them along the way. Most of this discussion will focus on great history of allocators found in user level memory allocation libraries. So we will discuss the details of what does actually malloc do. We knew that malloc is how we allocate heap, and the stock is automatically or automatic memory managed by us, by operating system, depending on our input. But for malloc library, we knew that it is tapping to a system called like SBRK to create or allocate memory. So how does the lower level mechanism and the policies of that work? So how does that actually work? We assume a basic interface such as that provided by malloc and free. Specifically, void malloc size t size takes a single parameter, size, which is the number of bytes requested by the application. So specifically, void malloc size t size takes a single parameter, size, which is the number of bytes requested by the application. So this malloc call takes actually the bytes that's needed by the application. So it is measured in bytes because that's how bits in memory are measured. It hands back a pointer of no particular type or a void pointer in C lingo to a region of that size or greater. So when the user program requests to this malloc API, it will return or hands back a pointer to that program of the same size that is requested in bytes or greater, because remember those then taps to the system call, which then system call allocate it the actual memory to us. The complementary routine void free void ptr takes a pointer and frees the corresponding chunk. So the call to free or void free to this library by the program takes a pointer and frees that corresponding chunk. So sometimes a program has a parameter or has a call to free. So this is how it is converted using this library, free void pointer, which means it's freeing that allocation of memory that was previously allocated to it. Note the implication of the interface. The user, when freeing the space, does not inform the library of its size. So when freeing that, remember when we created, when we use free after we allocate it in our code previously, we didn't need the exact size or the exact bytes because that would be time consuming. So we didn't need to provide that parameter to the malloc library. So the malloc library must be able to figure out how big a chunk of memory is when handed just a pointer to it, because he's the one who provided or allocated that memory. The space that this library manages is known historically as the heap. So the reason why it's heap, because again, heap is a priority queue, right? So the one that has greatest priority are being initialized. So you can think of that as such, like the algorithm we discussed in the previous video. So the space that this library manage, or the malloc, in the physical memory is called the heap, because what gets prioritized gets done. And the generic data structure used to manage free space in the heap is sometimes called is some kind of free list. So the free list, or in that space or region in that physical memory, are called in malloc library a free list. So again, we're just talking about the part of the process as a heap, because it's a user generated or allocated, and where most bugs get stuck, because for code it's really like a static variable, and for stuck it is automatic memory, and usually OS has something to do or some ways to overcome the issue with spaces or unallocated spaces. Now for the structure, we already solved that by segmentation, and now we're moving to our new, we're trying to solve that mechanism, right? And then in the next chapter we will discuss the pages, which actually has a fixed size allocated memory for this, that actually solve that, the structure, kind of like in data structure. In heap, if you use a heap, you automatically make a lot of things easier, because you just use the right structure. It doesn't need require you to come up with a good algorithm. So it's the same thing here. So that is called free list. This structure contains reference to all of the free chunks of space in the management region of memory. So on that allocated space of the heap, or this malloc, the data structure that is called the free list. Of course, this data structure need not to be a list per se. It doesn't need to be a list, but just some kind of data structure to track free space. We further assume that primarily we are concerned with external fragmentation as described above. Allocators could of course have the problem of internal fragmentation. If an allocator hands out chunks of memory bigger than the requested, any unasked for and thus unused space in such a chunk is considered internal fragmentation. So just like the reason why we do the segmentation, because there's an allocated space within the process, this is where the internal fragmentation lies. But now we're talking about the heap, the space provided by malloc in the actual physical memory, in how when we request like 15 bytes, though there's still 20 bytes in that part of memory, it can serve it because it's not contiguous. So that's what we are talking about here. Bigger than the requested, any unasked for, thus unused space in such a chunk is considered internal fragmentation, because the waste occurs inside the allocated unit, and is another example of space waste. However, for the sake of simplicity, and because it is the more interesting of the two types of fragmentation, we'll mostly focus on external fragmentation. So since we get the most back on space efficiency when we try to make the space allocation for that part, for the whole part of the heap efficient, then we're gonna focus first at that. Later, we'll relax that internal memory, unallocated memory, just like the per process memory we discussed in segmentation. We'll assume that once memory is handed out to a client, So this is another assumption. Once the memory or the memory allocated by malloc to the process, it cannot be relocated to another location in memory or in physical memory. For example, if a program calls malloc and is given a pointer to some space within the heap, that memory region is essentially owned by the program and cannot be moved by the library until the program returns it via a corresponding call to free. So, given a pointer to some space within the heap, that memory region is essentially owned by the program. So you cannot relocate that if there is a process currently taking over that, unless it's already free by the program and cannot be moved by the library. It cannot be moved by this malloc library until the program returns it via corresponding call to free. So until the program free it, doesn't mean that because some program, even though they're not using, so they're not running, they still occupies that space. So unless they're calling free, you cannot relocate to that space. Thus, no compaction of free space is possible, which would be useful to combat fragmentation. Compaction could, however, be used in the OS to deal with fragmentation when implementing segmentation, as discussed on the previous video. So in the previous video, we discussed how compaction helped with fragmentation, because you're compact, you don't allow unallocated space if ever. Finally, we'll assume that the allocator manages a contiguous region of bytes. So the allocator could not, like a node structure where you have this different space and not uncontiguous data. So we will assume that it's contiguous. In some cases, an allocator could ask for that region to grow. For example, a user level memory allocation on library might call into the kernel to grow the heap via a system call such as SBRK when it runs out of space. So just because, so another assumption that we will do is we assume that it's kind of like an array type of structure or space in the memory, on that part of memory where we only allocate via malloc as a contiguous space. And also, so once the malloc allocated a memory to a process, that process could initially require less value or less space than it started, but the system should be able to request the process should be able to grow its heap space, or the system, we will assume that the system could handle it whenever the space grows. So basically we should we will not assume that. So basically, to do that, you need to provide an extra space, of course, in a contiguous space to grow the heap. But since we're trying to optimize unallocated spaces, we will assume first, again, we will assume the better ones or the better conditions, and then we will relax it and make it more realistic as we go. That a region is a single fixed size throughout its life. Low-level mechanism. Before delving into some policy details, we'll first cover some common mechanisms used in most allocators. First, we'll discuss the basics of splitting and coalescing, common techniques in most any allocator. Second, we'll show you one can track the size of allocated regions quickly and with relative ease. So this is where the free list goes. So that space in the heap, that's free space provided in the heap by malloc, are provided here. So we will be able to, we will show you later or in the next videos how one can track that easily. Finally, we will discuss how to build a simple list inside the free space to keep track of what is free and what isn't. So we will discuss the algorithms or policies. We will to be able to track those free space. So after those processes that are allocated, we will build a simple list inside that space of memory to keep track of free space and keep track of what is free and what isn't. Splitting and coalescing. A free list contains a set of elements that describe the free space still remaining in the heap. So again, a free list contains a set of elements that describes the free space. Like here, this is free remaining in the heap. So since we assume that it's contiguous, we see this a contiguous element. So the free list for this heap would have two elements in it. 1 and 3 describes the first 10 byte free segments, bytes 0 to 9, and 1 and 3 describes the other free segment, bytes 20 to 29. So here, head 0 to 10, and then address. So as described above, a request for anything greater than 10 bytes will fail because it's not contiguous, and our condition requires to allocate a contiguous space. There isn't just a single contiguous chunk of memory of that size available. A request for exactly that size 10 bytes could be satisfied easily by either of the free chunks. But what happens if the request for something smaller than 10 bytes? Assume we have a request for just a single byte of memory. In this case, the allocator will perform an action known as splitting. So this is where splitting comes. It will find a free chunk of memory that can satisfy the request and split it into two. So this is how malloc actually allocate it. So based on that free space, it will split that and split that into two to satisfy those requests. In this case, 1 byte. The first chunk, it will return to the caller. The second chunk will remain on the list. Thus, in our example above, if a request for 1 byte were made and the allocator decided to use the second of the 2 elements on the list to satisfy the request, the call to malloc would return 20. The address of the 1 byte allocated region and the list would end up looking like this. So here, as you can see, 9, 0 to 10, and then addressed length 9, and started from 21. Since we returned the 20 to 21, since that there was a process requested for 1 byte. In the picture, you can see the list basically stays intact. The only change is that the free region now starts at 21 instead of 20, and the length of that free region is now just 9. Okay, because previously it's 10. So thus the split is commonly used in allocators when requests are smaller than the size of any particular free chunk. So this is where the split in low level mechanism happens. Basically, it divides that into two, or the allocator divides this free space into two, free available space or free available element, return that to the user, and then keep it the other one in the free list. So a corollary mechanism found in many allocators is known as coalescing of free space. So this is kind of like the opposite of splitting. Take our example from above once more, like 10 bytes. use 10 bytes and another free 10 bytes. Given this tiny heap, what happens when an application calls free 10 and thus returning the space in the middle of the heap? If we simply add this free space back into our list without too much thinking, we might end up with a list that looks like this. So here, it's not contiguous since we just free that allocated space from the process. So what do we do in this case to be able to serve higher space from the process? We do coalescing. So instead of splitting, we maximize now instead of dividing the free space, we will now add them up so that it can serve more space. So note the problem. Well, the entire heap is now free, seemingly divided into 3 chunks of 10 bytes. Thus, if a user requests 20 bytes, a simple list traversal will not find such a free chunk and return a failure. So let's say our process, our malloc our process requests 30 bytes, and malloc perform a list traversal. So list traversal is where you traverse through the list. You check all the available free elements. It will not find such. So that's what actually malloc library does. It's an algorithm as well. Whenever the program are requesting into it, it does this list traversal to find the free elements that can satisfy the program space request. What allocators do in order to avoid this problem is coalesce a free space when a chunk of memories is freed. So the idea is simple. When returning a free chunk in memory, look carefully at that address of the chunk you are returning, as well as the nearby chunks of free space. So before the this lower level mechanism, such as like combination of system and this malloc library, before it return that to the program or process, before it free that, it look first the address of the chunk it is freeing and the adjacent or nearby, because we assume it's a contiguous space. We assume we look at its nearby free space. If the newly freed space are sits right next to 1 or 2, as in this example, existing free chunks merge them into a single larger free chunk. Thus, with coalescing, our final list should look like this. So here, it can serve now a 0 to 30 because it looks on this beside 2 free lists beside it, and it combined them as 1. Then recalculate this address number in that heap. So indeed, this is what the heap looks like at first before any allocations were made. So this is where we start. With coalescing, an allocation can better ensure that large free extents are available for the application. So it makes available a free space again for the process or application. This discussion assumes that there are no headers, which is unrealistic for this variable size spaces, but simplifying assumption we make for now. So here's the example or the prime for the next topic we will discuss. So the header used by malloc library with a pointer, the 20 bytes return. So the we will discuss this in the next video, but the basic idea is that when we allocate or return a space to the process, we don't actually return just the process or the space. We actually also return the header. So we allocate the header, but we make it hidden to the process. The process only see the 20 bytes. So malloc does this in the background, or does allocators for this heap. So here we have the size 20, specific contents of the header. So this is also how we track it, the size of the header or the size of the allocated space for the heap.